Okay, our lecture today comes from section 5.7, curve fitting with quadratic models. So you can see the whole chapter we've been doing all different types of quadratics, from factoring and completing the square to quadratic formula. In this case now, we are going to be able to find a quadratic function that has exactly, or that exactly fits 3 data points. Or, even if I give you several data points. And then also find a quadratic model to represent a data set. So to start, let's ask these questions. If I said list objects or situations that could be modeled by a parabola, I'll start with some of them that we were dealing with last week. And that is the fireworks problem. I believe we also had something prior to that, and that was cliff diver. So what real-life situations could be modeled by a parabola, whether it's an upward parabola or a downward parabola? And then also think, how would you find the equation that represents the object or that situation? So as you look through things, and think about things you do in your real life, what would apply to that? We will have a little more in-depth conversation about that. But just the fireworks situation and cliff diving were 2 that came up so far. There are plenty of others. And let's see, obviously, in our class discussion, what we'll have. But knowing that you can have data values, data points, it says find a quadratic model whose graph contains these points. Now, the key word fitting was true earlier on when we tried to fit a model to data with lines, and I believe we're going to have the same situation here. If I give you something that has these 3 points and I want to be able to get an exact quadratic equation that fits these, there's a couple things we could do. We could write our generic standard form equation, y equals ax squared plus bx plus c, and then plug these a and x and y values into that, and we would get 3 equations with these 3 points. One for the negative 3, 16, one for the 2, 16, and one for the negative 1, 4. If we did that, we'd have 3 equations, 3 unknowns. We could do any of our systems. That's a little longer process by hand. Another choice, once we learn how to do matrices, we could solve with matrices. So that's 2 ways. The third way is with technology, which is the one we're going to embrace here, and that is look at these numbers. If they truly fit, and you're going to say, well, wait a minute, how can I tell if they truly fit? Well, usually the first thing you do is you draw a scatter plot. So we're just going to draw a quick scatter plot here. And actually, I didn't even give any negatives, so let's change that a little. Okay. So if we said that first one's negative 3, negative 16. So if I go over negative 3 and down to positive 16, we'd be up in here. Then if I went positive 2, which would be a little less, and then up 6, I'd be about there. Maybe a little less. And then 1, negative 4. So if I went here, and negative 4 would not be very high if that's 16. Okay, so I'm looking at that and saying, well, what do I have? Some people might say, well, that sort of looks like a little check mark, if you're thinking more like this. But if it's a little check mark, then we got to be saying, well, maybe that's a low point, or maybe that's close to getting a low point, and then maybe this goes up a little farther here. So it's definitely not a line, but we do have some kind of curve feature going on. So if you would go to your calculator, and we'll review this in class, and do our same procedure we did before with stat, edit, place your numbers in L1 and L2 on your calculator, Once you edit those, so we have our ordered pairs in here. Once you have those ordered pairs in, you can go back to Stat, Calc, arrow over, down and look at your choices for regression. This is best fit, and these are all supposed to be quadratic. It says find a quadratic function, so you have a quad reg in your list, choice 5. I believe our old choice, linear regression, was choice 4. This should be choice 5. So if you go there, and then arrow over, choose choice 5, again hit enter, you should have spit out your y equals ax squared plus bx plus c equation with your a, b, and c values. Okay? That is one we will double check in class, but with our regression, that's giving us the best estimate of your quadratic equation with these 3 points. Okay. From here, and in the reading also, there were several different diagrams of just data patterns. So if you look at this one, we have the number of rows, n, and the number of total dots, d. And it's a pattern. So when I have 1 row, I had 2 dots. 2 rows, 3 dots. 3 rows, 4 dots high, I should say. So 3 times 4 is 12 total dots. And then 4 rows across, but that made it 5 dots high, and 4 times 5 was 20. Now, if you look at those numbers, it's those D values we want to consider. So if I was making an XY table here, or in this case, an ND table, and let's do that. So ND, here's our values. So if we had a 1 and D was 2, and when N was 2, D was 6. When N was 3, D was 12. When N was 4, D was 20. And you can see from there, okay, so your X and Y values. So there's 4 points supposedly in a list. It says explain why a quadratic model is suitable for this relationship. In the book they described that if you look at your constant differences in the Y, so right now if we look on our Y values, 2 and 6, difference of 4, 12 to 6, difference of 6, 20 to 12, a difference of 8. Those are called the first differences. Now do that same thing again, differences, and we can call it the second differences. 6 take away 4 leaves us with a 2. 8 take away 6 leaves us with a 2. And it doesn't matter how many data pieces you have, you got to do the whole set. But right now we're looking at what we call our second differences. So these numbers right here, these are the second differences. And notice, every single one of them is a 2. They all match. We only have 2 of them here, but if the list was longer, we might have more. So when you do your second differences, because the second differences are constant, all the same number, they don't have to be all ones or anything like that, there will be a quadratic equation that models that data. Okay? So I think that's what we said for explain why a quadratic model is suitable. You could have graphed this also and taken a look at it, but second difference is probably easier than putting all those graphs there. Okay, so find the quadratic function for D in terms of n. And so again, these values, put them into your calculator. And let's just do this one sort of talking through it together. You can work on your calculator. I'll work on mine, and we'll see what we get. So head to Stat. We need to edit. So we're going to put these data pieces in. And this time we have 1, 2, 3, and 4 for our original values. Go up and put the Y values in. Make sure they're going into L1 and L2. And 2, 6, 12, and 20 for our y values. All right, from there we hit Stat again. We go over to Calc. We are looking for a quadratic regression, so that's choice 5. Hit Enter to say yes, that's what we want. You see y equals ax squared plus bx plus c pop up, but a is now 1, b is now 1, and c is 0 according to my calculation, which means if we use the calculator first, and you go with the y equals, it said a was 1, so 1x squared plus b was 1, 1x, plus c was 0. We really don't need to write it, or we could write plus 0. That would be the equation we would get with x's and y's. But notice our equation says find a quadratic function for d in terms of n. So all we have to do is go back in and substitute and simplify, and I think we'll be fine. So 1x squared would be the same as n squared, plus 1x would be the same as n, plus 0. We can leave it. So here is our quadratic equation that should match this data from our best fit situation. It says use this model to predict the number of dots in a rectangle with 15 dots on the shorter side. Okay, so total number of dots in the rectangle of 15 are on the shorter side, and that's really our n value. So we know n is 15. Do the math. Plugging into that equation, and you should be able to determine if n is 15, d is, and double check, you've probably done the math. Did you get 240? 15 squared is 225, plus 15 more, 240. All right, so there's another way. You could have even graphed those data points up here originally to see if it looked like it was quadratic, but since our situation told us, explained why a quadratic model would fit, probably the quickest and easiest is to do that second differences. Anytime there is a second difference, there is a quadratic model that should mirror that data. All right, what else? Remember, variables in the table represent a relationship. So that second difference we were doing, the constant difference in the consecutive x values results in a constant second difference in the y. So it's always the y's. If you have a constant difference in the x's, and so we did, go back and look at that for a second. We had a constant difference here, 1, 1, 1. So if your data pieces are constant, it doesn't have to be all ones again. It could be 2, 5, whatever, but as long as the number is the same, 1, 1, 1, 5, 5, 5, 2, 2, 2 in your x's, and then you can do your constant differences, you should be fine. So the other piece that it said there was we are going to be working with an acceleration due to gravity formula, and if you remember, we have seen this acceleration due to gravity formula a couple times now. And remember that h sub t that we've been seeing over here is just function notation. That is the same as saying y equals. And we want you to memorize this acceleration due to gravity because it deals with a lot of our real life problems. The firecracker problem mirrored that. The dive off the cliff mirrored that. So we should be able to use it quite a bit to calculate some of these real life situations. Now, double check though that you realize h sub t is the height anywhere in its path. So after x number of seconds, in this case after t seconds, I know the height of where I'm at. So I would put a t in. T equals time in seconds, absolutely. V sub 0 is the initial velocity. And n sub 0 is the initial height of your object. That leaves g. G, from science and math, previous knowledge, you should know that the gravitational constant is one of two things. In US units, it's equal to, well, it's going to be negative already. It's going to be equal to 32 feet per second squared. And in metric, it's equal to 9.8 meters per second squared. So it's just a nice constant number that you need to sort of have memorized as one you can use for conversions, etc., some of your calculations both in math and science. So that gravitational constant in US units, feet per second squared, in metrics, meters per second squared. All right. With that then, I believe we should be able to move on in this section and do a few best fitting situations with quadratic data. And they call it curve fitting because it won't be exact, but it'll be a very good fit. Make sure you just use all the data that you're given. Okay, that's all for now.